I'm Komei from Google Kubernetes engine. We have Keith here, UTL from Google Confidential Compute. Today we are giving a talk about GKE Hypercluster, a specialized orchestration layer we built for frontier of large-scale AI workloads. Yep. So before we look at the engineering, let's examine why confidential compute has become a very important, non-negotiable. I guess people already joined many talks today, so this is very repeated part, so I'll keep it short. Basically, our customers, they care their proprietary model weights, and also our customer care about their prompts, so they don't want their prompts to be exposed to both cloud provider as well as Kubernetes operator. So today we built the GKE Hypercluster to meet those needs, basically support the T in the Kubernetes platform, and I will jump in how we did it. So before we actually jump in the architecture, let's recap what's the standard Kubernetes gap we have between T and the Kubernetes. So when we try to run the confidential computing on standard Kubernetes, we hit many walls. So the reason is mainly because Kubernetes is designed in a way to share the resources, or we can say in the other word, the node, Kubernetes node is monolithic. So basically the guest OS runs a heavy local agent stack, which includes, for example, the kubelet, giving the admission API interface. Also, there are many daemon agents like the logging, monitoring, and also it gives the debugging shells. So this doesn't meet the minimum sync guest requirement for the T in general, as well as if we sync this from the TCP point of view, when we have TCP, we have to audit workloads, anything running inside the TCP, and this makes the TCP, if we make the node as a TCP, that makes the TCP very huge, so it's very hard to audit. Also, from the operator access point of view, as I said, Kubernetes provides the kubectl exec, and also admin have the capability to SSH into the VM you have. So there's no way that we are preventing from the both cloud provider and the customer's own Kubernetes operator from the accessing to node from the hardware point of view. And normally how this is done is using the policy. So Kubernetes does support the capability to harden your workloads or your nodes so that you cannot easily access. For example, we have the access on demand, so our operator can only get into the node when you approved, but that's still not enough to provide a T here. And also from the measurement point of view, we have the confidential node, which provides the basic measured boot, but that one only stops at the OS kernel, VTPM, and the loader. It doesn't actually measure what the actual workload is running, which is actually an essential part for the T. So how did we solve this? Our solution to these hurdles was basically to have the decoupled architecture. We called it linked runner model. So instead of forcing the runner nodes to run the full Kubernetes stack, we split them into two. So the left side you can see is the traditional Kubernetes control node. It runs the kubelet, containerd, and all other system daemon set. The actual AI workloads are stripped down into the other node. We call the sealed VM, which has run the minimum set of the software, and also they're all measured. So here we only need to run the scene layer of what we call the launcher agent, as well as the containerd, so that you can spin up the pod. So we basically touring down all the monolithic K8s node, Kubernetes node into two, and split them into the untrusted Kubernetes node, which runs the same way as the current Kubernetes node, and also dedicated sealed VM to run your AI workload. Yep. So let's look at how this works under the hood. So when the GKE control plane actually scheduled pod, when you create a pod, the GKE control plane will create a pod, and the kubelet pulls it into your node. This is similar here as well. So this layer doesn't change as from the API point of view or user interface point of view, it works the similar way as well. But in the normal way, the pod will actually schedule on the control node, the left side untrusted node, Kubernetes node. But in the GKE Hypercluster, we basically proxy that into the sealed VM we talked about. So there's no Kubernetes running on the runner. And how do we do that? So we built the layer called the CI proxy. When the pod that needs to be run in the T is scheduled on the actual Kubernetes node, the CI proxy basically will proxy the CRI API call to the launcher agent in the sealed VM. And the sealed VM will actually start up the pod and containers inside the sealed VM. So from the developer point of view, this is still conformant to the pod topology or the semantic. So all the work you do, scheduling pod, all those works the same way. And yeah, let me see. So we also, when we schedule in pod, we also have to bridge in the pod networking. Because a lot of Kubernetes features are built on top of the assumption that the pod IP is the one working underneath for each pod. And then, for example, that's how you have the data plane eBPF layer, and which supports the network policy. With this architecture, we also need to support the pod IP so that all those Kubernetes features will work the similar way. Well, how we did it, basically, similar at the layer, when we create the pod network namespace in the Kubernetes node the same way as well. So basically, all the pod network from the control plane point of view still exists in the Kubernetes node. Then we actually built using the Linux networking feature, Geneva tunnel, to tunnel the traffic to the workload running inside the sealed VM. So data plane network traffic routes directly via the data plane v2, and which is also wrapped via the VPCSC perimeter in this case. And so given this one, all the pod network works a similar way. And if you have any Kubernetes networking feature you're using for your AI workload, will work exactly the same way, including ingress, networking policy, as I said, and also the service, Kubernetes network service. So I talked about the pod networking, and now let's also dive into the general networking VPC setup for this architecture. So here we have 3 networking taking place. One is the pod network or the cluster network, basically your standard Kubernetes node connecting to your cluster control plane. This is where you get all the Kubernetes traffic and the control traffic to your Kubernetes node. And then we have this shim network we called, which is actually the network connecting your standard Kubernetes node and the sealed VMs. This is also the networking tunnel used for the networking tunnel I mentioned before. Normally, this network is isolated to the connection only, so it's not exposed to internet, and also it's also controlled by the firewall, so it doesn't reach to any outside of the even the Google services also. And since I said this is for the AI workloads, a lot of time you also need additional networks for your AI workloads. That's the third one on the right side. This is also dedicated to the linked VM, the sealed VM side. Basically, you can use it for high bandwidth traffic if you need really high speed for downloading your model weights. So you can use this network, and this is isolated from your untrusted Kubernetes layer as well. And here, if you have to use to access for example, Google Cloud Services, you do set the VPCSC, so make sure that all the needed security is there. All right, now I'll pass to Keith.
Great. Thanks, Komei. So Komei has talked a lot about what had to change in Kubernetes to kind of split out the pod into this separate environment and take the regular Kubernetes like node work and have it be in an untrusted space. So let's zero in instead on that trusted space, the TE aspect, the linked runner or sealed VM that he mentioned before. So inside of the sealed VM, what we have is a stripped down, measured, and fully untested environment that builds up to a commitment of having 0 operator access. This is what makes it like a true TEE. Some of you may or may not be familiar, but a few years ago we did release our, Google Cloud released the confidential space product that has these features. And actually what we've done here is taken that same baseline, our attested container optimized OS platform, or ACOS. And that is the basis for the confidential space TE, and it's also the basis for the sealed VM here in Kubernetes. You may have noticed in the keynote earlier this morning, Nelly also mentioned that we use confidential computing to protect Gemini when it's running on-prem through Cloud's GDC product. And this is really us kind of putting our walking the walk instead of just talking the talk. We're using the same ACOS platform to protect our IP when it's running in your environment. So that's how we are trying to let you know it's okay for you to trust your IP running in our environment because it's the same controls. We trust it to protect Gemini. Now, with ACOS, all of the normal administrative pathways, whether they be the kubectl exec or SSH or the cloud guest agent, these pathways are all gone. They're just not there. And instead, the only influence you have is through a kind of curated, limited set of input parameters to tell it what to run and what to launch. So, and all of these things that influence the execution of the job are all part of the attestation. So even people that have full administrative access to either the GCE or GKE control planes here, none of them can change that commitment to having 0 operator access or the signature of the workload that's been launched. Once it launches and it's running what it says on the 10, and it's not running anything else. Now, like any good TEE, you aren't taking our word for it. Throughout the stack here, we have measurements coming from multiple independent trust elements that we have. And a lot of confidential computing really talks about the guest layer, the CVM. That's a very important part. It's a very valuable part. But things actually start much lower than that. What we have in this product is we start with the Google Titan chip. This is the same security that is embedded in Pixel phones and all of our servers throughout Google production. And this serves as our physical root of trust that establishes the machine as a legitimate Google hardware running in our data center. And also outside of the guest still, we are locking down the host operating system using TI, the Titanium Intelligence Enclave. And all this builds up to the point where we have the actual guest itself. And with the guest, there are options here. You can be using our shielded VMs. Now I mentioned those earlier, with a VTPM as the root element of trust. And also confidential computing. So you can have AMD Sev also using a VTPM, or moving on to having the trust be in the CPU itself with things like Intel TDX. As Komei just mentioned as well, the drive for this product has largely been coming from AI workloads, and AI workloads, they need more processing power, more oomph behind them. They need accelerators. So for those accelerators, if you're running on Intel, you do get the AMX extensions right out of the box, but with GPUs and TPUs, those also are supported being attached to the hypercluster. So in that, they have their own trust elements with confidential GPUs. And what this really builds up to in the end is a remotely verifiable set of evidence that shows that the environment is living up to that promise that I introduced before, that there's 0 operator access, and that the integrity of your workload has been maintained.
Yeah, thank you, Keith. So we talked about how we have the no operator access in the T or sealed VM. Let's also talk about how we prevent Kubernetes operator malicious one can schedule workload and that getting scheduled workload into the T. So what we have here is, so as I said, the GKE control plane in general or Kubernetes operator is treated as untrusted in this model. So they can attempt to inject malicious configuration or anything via the pod spec. To prevent this, so we have the launcher agent we build into this policy layer, or you can call it, think it as an API gateway defense. So the policy actually takes the customer provided policy, which defines the shape of your workload. You can say, for example, you're not allowed to change the container execution path. You're not allowed to change the environment variables. Those things will be, you can specify that in your T policy. And when the container is actually scheduled, the launcher agent will be evaluating your pod spec and container spec against the policy you provide. So anything that's not conformant to the policy you provide yourself will be get rejected. So the container will not launch at all in this model. Okay. And we also enforcing the code level integrity with this model as well, with the cryptographic launch. So not only the pod spec, we also support your container image to be signed by the your CI/CD pipeline. So the same T policy actually can take your public keys you use to encrypt your container image or sign your container image. And when the container is loaded in the T, we also, before we launch in the T, we verify the signature assigned by the public key you provided. And whenever if it doesn't, the public key provided is not right, or you're missing the public key in your T policy, we also deny the boot of the container as well. So with this mechanism, you can prevent malicious workloads that's not defined by yourself to be scheduled by the malicious Kubernetes operator.
So what's on the screen now is really an example of using the attestation to get to kind of the heart of the issue here, and that's secret release into this environment, because you want to establish the trust that the environment is what you expect it to be before those secrets ever enter it. So what's shown here is the kind of the happy path, the easy button that we provided to integrate with Google services. So we do support taking the attestation evidence that I described earlier that has different parts of the stack measured and included there. It integrates with our Google Cloud Attestation service. That Google Cloud Attestation service processes that evidence and gives you back a digested, easy to use kind of an easy to write policy around set of claims about your workload that is something that you can put in your IAM access configuration for your KMS keys. That makes it really easy for you to be able to say, I want this data or this key that has my secrets encrypted with it. The only thing that is able to decrypt using that key is the workload that I've written, the one that I expect to be deployed, and only if it's running without administrator access in the TEE. Now, to decouple yourself from Google as the cloud service provider, you can also use your own versions of these. You can be using KMS or IAM systems elsewhere and the attestation verification. So what we've really tried to do with this is create a collection of best practices, an easy to use way to have a TEE platform with a clean separation between what the platform can provide and what you yourself care about, which is your business logic that needs to run inside of the TEE. Once your pod is running, it can behave like a normal application does. It should still do things like authentication and encryption to keep your application layer logic secure. But now it has this extra information, the attestation, to be able to help you with that. that process, to integrate it in where it's most critical. With this, we really have taken, we started with our confidential space platform a few years ago, and brought together this with Kubernetes to have extra ease of use.
Yeah, so far we focus mostly on the confidential compute or security side of this architecture. I just want to say this actually has a scaling benefits as well. So as you can see, as I mentioned, we are decoupling the workloads with the Kubernetes node. So this actually brings us to, for example, 1 to 64 mapping of the standard Kubernetes node to the workload sealed VMs. So reduces actually the GKE control plane workload because there's not so many Kubernetes nodes needed for the GKE control plane to process anymore. So this actually gives us the 64 times the API server relief, and also we have our design partner validated with this scale working for their workload, hyperscale workload as well.
Yeah, so putting all this together, what this has done is, we've talked throughout this, is we've minimized the TCB. We've shunted off the pod into this tightly scoped, secure environment, and locked it down and had an attestation around it. And we keep the goodness of Kubernetes. Everybody knows Kubernetes, everybody uses it all over the place. And you're able to still have that integration, still have that familiarity, and have it be part of your business deployment model. And we've kept this like zero operator kind of proof around your data as a hard enforced cryptographic attestation. So yeah. So with all that together, what Komei was bringing before, we have a really easy to use secure TE. So I think we timed it pretty well. We were shooting to have a few minutes left for questions, and we have 2.5. So any questions?
No.
And the actual Kubernetes node, are they localized? Is the locality relevant as you connect them to a network?
Yeah, they're connected via the network. So that's the 3 networking model I showed VPC. So there's a dedicated, we call the shim VPC in between to connect them. And that's a more isolated network you'll use.
They aren't co-located on the same physical machine, if that's what you mean, but they are located in the kind of high bandwidth locations to each other.
So latency is observed in latency.
The latency is ignorable so for in normal case, you put them into the same zone or same region, and the latency in the data center network is likely less than 5 milliseconds.
Yeah. Yes, in the back. We don't use Hypercluster specifically. The baseline of the TEE, the ACOS operating system, is common between Hypercluster on GKE, confidential space, and Gemini on-prem.
So you feel like using the model weights in this feel comfortable with it sitting in just different enterprises?
Sitting in different, what was that?
Like companies.
Well, we do it. GDC is a product. We have Gemini running out in the wild. So, yeah. You take that one?
Yeah, that's a good question. So the storage, if you need to share, it's hard to be handled in this case. So in this model, you cannot share the model, the storage. So the storage is actually attached to the sealed VM itself. So normally how we handle is it's either need to be connected via the networking. For example, we have the Google Cloud Storage GCS Fuse. That's the more networking based feature. Or we can have the more local SSD, which needs to be attached to the VM from the beginning. So those will be supported. Yeah.
And to clarify, when he was saying that like sharing between pods, since they're not on the local machine, we can't just mount the same path into 2 different pods anymore. However, you still do have other methods of, you can use any storage mechanism that is across a network, like GCS. So.
Yeah, you can still use those.
And since it wasn't on mic, the config secrets in Kubernetes is what the question was there. And yes?
How much of that is already available?
It is already available product. So if you have question, you can.
So I can do today attestation verification for release secrets for SMP, TDX.
So I was going to say that not everything on all the slides are currently available. Yes, so. I don't think we can fit that in the next 40. Oh, we're 40 seconds over. So negative 40 seconds. I can't cover that. But we do support confidential VMs with TDX. Today, we don't yet have platforms capable of CCA. That's on the slide as something that in the future, and also with SMP. There would be SEV, but not SEV SMP today.
What's your startup latency? How fast is the VM?
The VMs are, so the question was how fast the VM can boot up. So this is same as the control plane boot up. So these VMs are basically GKE VMs. So in our model, you normally, since it's for the AI workloads, you normally provision those with a reservation app. For example, it's a TPU or GPU, so you have provisioned them. And then you will have to use, you schedule the workload the same way you create the pod, and then the pod will get provisioned. So we didn't handle that problem in the VM provision problem in the Kubernetes layer. It's still the problem for the GKE control plane layer. So use the GKE control plane to provision the VM, sealed VMs as well. Similar to you provision the standard Kubernetes node.
All right, we are 2 minutes over, so I think we're going to have to cut it off here, but both Komei and I will stick around here or out in the vestibule or whatever for further questions. Okay? Thank you for your time.